How was chapter 6 homework?
Good.
Do we all feel like we've mastered 6? Yes. Anyone like not sure about 6? Because here's the kicker. Remember in chapter 4 when I taught you probability and I got you to understand the table, and then I taught you Bayes' theorem and I said I'm going to get you back to the table, right? And then we could answer all those questions. So in chapter 6 you get chapter 6. I'm going to start by saying I think most students do not like chapter 7. But I'm going to get you back to chapter 6. Okay, so I'm going to do something and get you back to chapter 6. Okay, so if you understand chapter 6, right, draw and shade the area you're looking for, calculate the z-scores, look the areas up in the table, and manipulate it to find the area. I'm going to get you back there. But first we're going to have to do something else first. Because in chapter 6 we were talking about the probability a person makes more than this much money, a probability if you run a race you were in the top 10%, right? What's the probability you're in the top 10%? The difference with chapter 7 is we're looking at a group of people, we're taking a sample and we're going to look at the probability of the mean of that sample, okay, rather than an individual score. So let's say we were talking about how long you want to take a test. Remember we had a question something like that. We had a question that told you it would look like this, and the average person takes 80 minutes on the test. Remember that? And the class is 90 minutes long, but some people wanted to take longer. Remember that question? So this would be the probability a student can't finish. So if the class is 90 minutes, and we say, what's the probability a student can't finish? That's a chapter 6 question. Okay? That's a chapter 6 question. A chapter 7 question would be, you take a sample of 5 students, what's the probability that their mean is more than 90 minutes? Okay, well that's different. That's a different distribution. If you think about it, let's say that there might be one student, I forget what the standard deviation was. It was 10, wasn't it? So, so if this is at +3, one student wants to take almost 2 hours. One student. And one student's done in 50 minutes, right? And there could be a little outlier here and here. Okay? But let's say Colton, he's the one who wants to take 110 minutes. Nobody else wants to take 110 minutes, just Colton wants to take 110 minutes. Okay? So if I take a sample of 2, maybe Chris's takes the second longest. Chris wants to take 108 minutes. If I take a sample of 2, the highest that the mean can be is 109. It can't be 110 anymore because there's only one of him, right? So the average is going to be 109. These 2 are the fastest. Mylene wants to take 50 minutes. Kira wants to take 52. Now the lowest I can get is 51, average them. So when you start to take samples, if this is what the original underlying population looks like, for any individual sets of students, if I take a sample of 2, the distribution gets a little bit narrower and taller. Because the area has to stay 1, right? So if you squish it in, it's got to go up. So if n was 2, it would look like that. How about if n was 3? Right, now I can't get 51 and 109. Now we're going to include Brandon, right? And now we've got a different number. But as you take a bigger sample, the bell gets narrower and taller. How wide's a bell? In general, how wide is a bell? How wide is it?
6 standard.
The area under the curve is 100%, but it's 6 what?
Standard deviation.
6 standard deviations, right? It's plus or minus 3 standard deviations. This is 6 standard deviations wide. So as I'm taking bigger samples, what's happening to my standard deviations? They're getting smaller, right? There's less scattering because you can't have these extreme values anymore. Okay, so that's going to be the difference is what I'm going to do to get you back to the place that you're going to like, which is chapter 6. We're going to have to do 3 things. First of all, it's not, in chapter 6 it also told you it was bell-shaped. In this chapter it's not. So So number one, we're gonna have to prove that it's bell-shaped before we draw it. And then, you're gonna draw your bell, like we always do. And then we're gonna have to calculate a new standard deviation, okay? Because we said it got smaller, right? So we're gonna learn how to calculate a new standard deviation. Once you've done this, you are back to a chapter 6 question. You've just got a new standard deviation. You've got to prove it's bell-shaped. You've got your new standard deviation. Now you can draw and shade the area you're looking for, calculate a z-score, right, which is the number minus the mean divided by now our new standard deviation, and then look that up in your booklets and move on, okay? So that's a brief overview of what we're doing today. I'm on clicker. Today we're going to talk about means, okay? And next class we're going to finish chapter 7 and we're going to talk about what are called proportions. So this is called a sampling distribution. So a couple things. Remember, population means all elements of interest, not necessarily the population of the United States. Could be registered voters in Scottsdale, it could be whatever, right? And a sample is a subset of the population. So for example, I see that there's lots of school bond election signs in Scottsdale. Have you seen those hanging around the street corners? Not that I'm hanging around the street corner, the signs are hanging around the street corners. So, and I see when I'm stopped at the stoplight, right, it says vote yes on 1, 2, 3. So if they want to find out if they predict that this is going to pass, they might take a sample of registered voters and ask us, do you plan on voting yes or no, or do you not plan on voting at all? So they would take a sample from the population. The population of interest would be only Scottsdale registered voters. If you live in Scottsdale and you're not registered to vote, they really don't care what your opinion is because you can't vote, it's too late, right? So they would only look at the population of interest and then you take a sample. So that's important that you try to get a really good sample, because they will use that information from that sample to infer things about the larger population. So if they take a sample of 500 Scottsdale registered voters and they find that, 62% said they're going to vote for the school bond, then they would assume that that school bond is going to pass. Okay? And if they think there's something overwhelming like that, if it's 62% is a lot. So if they think there's an overwhelming, guess what? They'll stop spending their money on advertising that campaign. And they'll put it into another campaign that maybe needs more help, right? So they use this data to inform your decision making. So I've got 62%, okay, they slack off a little bit. And you see that in the presidential election when the presidents always go to the states that are borderline. Occasionally they show up at somewhere that there's a slam dunk, but really to raise money, not to get more voters. But they do that. They go where they're gonna make an impact. So they take this. It's a misnomer. It's not a simple random sample. It should be called a very difficult random sample. Because a random sample, by definition, is everybody in the population has an equal chance of being selected. So if I wanted to pick 2 people from you guys, it's easy for me to put all your names in a hat, shake it up, and pull 2 out. You all have an equal chance of being selected. But it's not so easy to do that with Scottsdale registered voters. Because what do we do when people call us and ask us to participate in a survey?
Hang up.
We hang up, right? In the back in the day when you were little, and we had landlines, right? And they would call us on our landline at dinner time. Always when I'm cooking dinner. Why? Because they know you're home, right? And so always cooking dinner. Do I answer? Absolutely no way in heaven, right? I'm cooking dinner. I have 4 screaming children, And so am I gonna answer your survey? No. Who does answer the surveys?
Older people.
Older people who look for someone to talk to, right? I remember when my kids were little and it was like 120 degrees out, I'd sometimes take them to Paradise Valley Mall. They have that little indoor play place. Anybody play there? that little indoor play place by Paradise Valley Mall. And there's always someone standing there with a clipboard. And I avoided them like the plague. They will ask you questions. And if you qualify, you can go in the back room and I think you get like a $10 gift card to the mall. I have 4 screaming children with me. $10 ain't gonna cut it. You know, I do like a massage, a spa day. I don't know. You're gonna give me a lot of stuff. I'm not. So who does it for $10? Sometimes older people because they want to talk to people, but who would do it because of the $10?
Young people.
Yeah, the young kids at the mall. They all wanted to do it because they got money, right? $10 for 45 minutes of my time. Yeah, got to be kidding me. So they would get a distorted survey. Because they got the young people who will take the $10, they got the old people who want someone to talk to, but they might not get a really good random sample. So it's very difficult to get a random sample unless you have a captive audience. Like, you know, you say, okay, sometimes they have surveys our institution does, and it's like a national level thing. And certain students are some of you could get to be the lucky winners, but I have to give you time in class. Because the survey takes 45 minutes. So if I would get this packet, and it'd just be like, you know, you gotta take the survey. And so it's kind of because I give it to you in class, a captive audience. But, you know, otherwise it's very, very hard to take a simple random sample. And you've just got to make sure, you know, sometimes you think you're including everybody, but you're not. You know, like even if you randomly dial people, you're only getting people who have phones. There's homeless people. You've lost, you know, if you want everybody's opinion, you lost a whole segment of the population. How about if I use the phone book? Who's in the phone book? None of you, right? Because you're not in the phone book with your cell phones. We used to all be in the phone book. You used to be able to do that. I used to be able to look you up and find your address and your phone number. So you can't do that anymore. So it's very hard to do a random sample. Just know that. Okay? It's very difficult to get perfect information. All right, you're going to see the term point estimate in a lot of homework questions. And a point estimate is when you use one number to represent another. Okay, that is different in the next chapter. We're going to talk about confidence intervals as estimates. But here we're just using one number. And that is, if I've got the sample mean, I use it as the point estimate for the population mean, right? I took a sample, the average salary was $60,000, therefore I think the average salary of all Scottsdale, whatever I surveyed, was $60,000. So you use one. You can also do it backwards. You can also have the population mean and use it for the sample mean. For example, if I am a big company with lots of employees and I've got, you know, 500 managers, and I know that on average they make $100,000 a year. And now I'm speaking to 30 of you. My best guess, you make $100,000 a year, right? So that way I know the population mean, and now I'm applying it to the sample. So it can go either way. X bar can represent mu, and mu can represent X bar. We talked about that when I talked about opening my doggy bakery at the mall, right? And I said, 60% of the entire population has a dog at home. So I would assume 60% of my sample would have a dog at home. All right, S squared is your sample variance, sigma squared is your population variance. S is your sample standard deviation, sigma is population standard deviation. This is a new one. P with a line across the top. P bar. Sample proportion is a point estimate for P, population proportion. So for example, okay, that is about, do you have a dog at home? Okay, so if I asked 20 people, do you have a dog at home? And 10 of them said yes, 50% would be my sample proportion. The 0.64 or whatever it really is that's on the Humane Society site, that's the population proportion. That's of everybody in the United States. So why, I told you today I'm going to do means and next class I'm going to do proportions. Why would I why would I ever do proportions? Why don't I just do means? It's so much easier. I know what a mean is since I was 8. Why would I not do means all the time? When do I have to use a proportion?
When there's like too low number or too high numbers, too much between.
No. Do proportion. I'm going to give you 2 examples when I'm going to use proportions. Okay, and so I'm going to use proportions when I ask you if you have a dog at home. I use proportions when I ask you, are you going to vote for the school bond? I would use a mean if I ask you how many dogs do you have at home. Yes,
But it's
Grant.
a binomial, like either, like it is or isn't.
Yes, it's not, yeah, it's categorical. Because it doesn't have to be is or isn't, because you could say I'm not gonna vote, I'm gonna vote yes, I'm gonna vote no. So that could be 3 options. But I use proportions when I have categorical data, and binomial, that's an example of it. So binomial, there's only 2 options, but with voting, there's 3. I'm not gonna vote, can't be bothered to go. I'm gonna vote yes, and I'm gonna vote no. So there's 3 options. So you use proportions when you have categorical or qualitative data. You do means, you can only do means on numbers. I told him yesterday, I was like, so when I'm doing about, are you gonna vote for Trump? So I said, you know, if you call and ask, you know, who you're gonna vote for, did you vote for in the presidential election? Someone voted, I voted for Trump. I'm like, you don't have to tell us that, that's private. So, but I said, you know, if I call you and say, did you vote for Trump or Clinton? You can't average that, right? That doesn't make sense. I told him you'd have a clump. You averaged Clinton and Trump, you'd have a clump. And so that's why it's qualitative. You count how many yeses and nos, or you didn't vote, and that would be a proportion. Because when I say who did you vote for, you would tell me who you voted for. It was not a number. So here's a very quick question. Chapter 7. Windows down. Alright, here's number 8. It says a survey question for a sample of 150 individuals yielded 75 yes responses, 55 no's, and 20 no opinions. A, what is the point estimate of the proportion in the population who responded yes? So a point estimate is use one number to represent another. It's like, right, so it's because you don't know the proportion of the population, you've got to estimate it. So what number would you give me as your best estimate? 50%, 75 divided by 150, right? So to come up with your proportion, a proportion is x divided by n. So in this case, n is my sample size, and x is how many of them had the attribute you're looking for. A proportion is always between 0 and 1. If I say, what proportion of the pie did you eat? You can eat none of it. Maybe you ate all of it. You could have eaten 50% of it, right? A quarter of it. You can't eat 3 of it because there's only 1 pie. Okay, so a proportion is between 0 and 1. This is a chapter when it's going to be really important when you draw your bell curves that you keep your numbers here, your z-scores here, and your areas in the curve. Because your proportions, when we do proportions next class, are going to look a lot like areas. Because areas are between 0 and 1, and proportions are between 0 and 1. And you don't want to start subtracting the wrong things from each other. Okay, so you keep your proportions, which will be your numbers here, your z-scores here, and the areas in the curve. Okay, so this is where your attention to detail is going to pay off. All right, and then the proportion who respond no would be just what? Right, so this would just be 55 divided by 150, which is 0.366 recurring. Okay, is everybody good with that? That's how you get a proportion. If you called 200 voters and 120 said they're going to vote for the school bond, what proportion say they're going to vote for the school bond? 60%. 120 out of 200, exactly. That's exactly right. All right, questions about that? Okay. So now we're going to move on to the theory bit to get you to chapter 6, okay? So, whenever you take a sample, it's probably not perfect. Hopefully it's good enough, but it's probably not spot on, right? We found that out at the last presidential election. My class at the time, we followed 16 different organizations that predicting the results. Out of the 16, only 2 of them, the day before the election, thought Trump was going to win. Okay, 14 were wrong and 2 were right, which has called into question a lot of our statistics, because it was how big was their sample, and how did they poll, and how did they get a good sample, because most people did not call it right, and that was it's not the first time in history. Back in the, okay, you probably know American history better than I do. Dewey, heard of him? Who did he run against? No, it's older than that. Have you heard of Dewey? There's a newspaper, it said Dewey wins.
Oh,
I think he ran against
It
Truman.
was Trump.
Yeah, I think he ran against Truman. And they had to print the newspapers in the olden days, and they hadn't finished counting, and they printed the newspapers that said Dewey wins. But when they actually finished counting, Dewey didn't win. Truman won. And so, it's not the first time in history that it was predicted wrong, but it did call into question a lot of our statistics. Whenever you take a sample, by definition, there is sampling error attached to it, because it's not perfect. And sometimes you find out that you're not perfect, like when you finish counting the votes, right? So when they thought that Clinton was gonna win and then Trump won, well, they found out they were wrong. But what if you collected data and you said, should we open a store over here? And you collected data and you said, no, it's not gonna be successful. You'd never know if it really would have been, do you? Right? So sometimes you find out what your error is, and sometimes you never find it out. It just depends. But just know, whenever you take a sample, you've got to know in your head, there's a chance you're wrong. So a lot of times in stats, we talk about being 90% confident, 95% confident, and 99% confident. Okay? If I'm 95% confident, this sounds pretty great. That means 5% of the time I'm wrong. That means every 20 decisions I make, one of them is wrong. And it's another reason why I want you always to back up your work with your data. Because if you do that in the workplace, and you're wrong, and you lose money on your decision for your company, you better be able to back it up why you did what you did, so that you don't get fired. Okay? Because by definition, statistics come with error. They're not perfect. Hopefully, they're good enough. They don't completely change your decision. Okay? So sampling error is just the result of not using everybody, not asking the entire population. However, note this last thing right here. Your error will go down as your sample size increases. So think about our example earlier with the test. Okay? It doesn't matter if Colton wants to take 110 minutes and Mylene took 50. But I had really extreme, if I had just taken a sample of 2 and I happened to pick these 2, and oh my God, the class must take 109 minutes. The class is only 90 minutes long. But if I got these 2, I'd be like, oh my goodness, I have to make the exam longer. They only want to take 51 minutes. I gotta make it longer. Well, that was way off. Both of those, if I had picked you two randomly, and you're just as likely as any other, right? I always tell people, the lottery is just as likely to be the numbers 1, 2, 3, 4, 5, 6 than any other set of numbers. Every group is just as equally likely. But if I had sampled out of all of you, if I had sampled 24 out of 25 of you, it didn't matter if I included the 50 or I included the 110 or left them out, my mean would be pretty darn close to the population mean if I sampled any 24 of you, right? Because the bigger the sample, the smaller the error rate, because I'm leaving out less people. So I've got more data. Okay, so you have to understand this inverse relationship. The bigger the sample, the smaller the error, because you've got a better data set, a more accurate data set. All right, so in chapter 5, when I asked you for a probability distribution, what did I want you to give me? What's that? No, that's in chapter 4. When I wanted that probability distribution in chapter 5 was, remember, discrete probability distributions. And we did regular, discrete, binomial, and Poisson. Right? And when I asked you for probability distribution, I said I want a list of all of the outcomes and their associated probabilities. We did like televisions. And they sold, 0, 1, 2, 3, and 4. And then we had these probabilities and we listed them and they summed to 1. Remember that? That's a probability distribution for discrete. In chapter 6, we didn't feel like we wanted to list all of them. Why not?
Take two forever.
Yeah, it would take forever. They were like infinite, right? So how much gas do I buy when I go to the gas station? Could be many, 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 many infinitely different amounts. So in chapter 6, when I asked you for a probability distribution, you needed to draw it, mark on the mean, and count and the standard deviation, right? And that was your probability distribution. And I could go and I could find different areas in probability, because area is probability, right? That was a probability distribution for continuous data. So in chapter 7, we're going to do a probability distribution for samples, right? For all the means for the first one, we're doing quantitative data. So we're trying to do, what would the distribution look like for all the different means that I could get? Right, so it's going to be these red ones. Like if n was 2, that would be my sampling distribution. Okay, so we're going to do a question in this chapter. It's about a company that has 2,500 managers, and you're going to be taking samples of 30. Okay, and when we're doing mean information, we're going to learn about how much money they make on average. And we do proportions, so the mean's going to be a dollar amount, right? Because you average dollar amounts. I think it's going to be 51,800. And when we do proportions, it's going to be talking about whether or not all these managers have attended our management training program. Okay, so I say, have you attended the management training program? And you would answer yes or no, right? So they are going to tell us that 60% of the people have attended their management training program. Then we can infer things about this little group of 30 that I've got here. How much money they make and how many of them have been through the program already and how many haven't, okay? So you would know, if I know on average $51,800 is how much my managers make, and I've got 30 of you here, what's the best guess at how much money you guys make on average? 51,800, isn't that my best guess? Is it going to be exactly right? No, probably not, because you're only 30 out of 2,500. But it's my best guess that sample mean here is going to be the same as the population mean. Okay. So when you're doing a sampling distribution of X bar, that's what you do for means, right? You're going to show all the possible values of X bar that I could get. So that is, I'm going to jump a little bit on it. That is, if I haven't proved it yet, but let's say I've proved it. If I decide that on average, the managers make this much money, okay? The managers make this much money, this distribution is gonna say, when you take a group of 30 people, what are all the different values of X bar you could get? Well, that's the most likely, because that's the mean, right? But I could get something down here or something up here, couldn't I? Yes, right? So this is gonna tell me all the different values of X bar I could come up with if I took a sample of 30. Okay, so the expected value of is mu. Your mean, my best guess is it's mu. If I said 60,000, that's why? Why would I say 60,000? If I know that my average manager makes 51.8, my guess on average will make 51.8. That's sensible? So the sampling distribution of X bar, mu is in the middle. That high point right there. Oop. Okay, so this is how we said that, I just erased it, but the reason the distribution got narrower and taller was because the standard deviation is getting smaller, right? This is how you calculate the standard deviation of X bar. It's the standard deviation of the population divided by the square root of n, your sample size. Therefore, the bigger your n becomes, the smaller your standard deviation of X bar becomes, right? When you divide by a bigger number, like 20 divided by 2 is 10. When I do 20 divided by 5, now it's 4. That's gone down because I'm dividing by a bigger number. Okay, so your standard deviation of X bar is also called the standard error. I'm going to call it that because it's easier than saying standard deviation of X bar. I'm going to call it the standard error. So that will change every time you change your sample size. I said n was 2, it would look like this, and n was 3, now it's taller and thinner, n is 4, now it's taller and thinner, because the bigger n becomes, the smaller the standard deviation becomes, the smaller the standard error, or standard deviation of X bar becomes, the narrower the bell and the taller it becomes. Because every bell is how wide? 6 standard deviations, right? So 6 of these wide. So the smaller you make this, the narrower and taller the distribution becomes. Okay, everybody got any questions about that? Because it's a bit of theory until we get back here. Okay, all right, so this is what you will do most of the time, this formula. However, this is a reward. You might feel like it's a punishment, but you get a reward to include in your calculations. This is called the finite correction factor. It's a reward, it's not a punishment. And you get to use it if you take a sample that's at least 5% of the population. It's your reward for taking a big sample. It means you've got great data. You have great data, I think your error rate's gonna go